For generations, automotive engineers have worked under one assumption that seemed impossible to escape. If you wanted steel to become stronger, you had to accept that it would also become harder to shape. If you wanted it flexible enough to form complex vehicle parts, you had to give up a measure of strength. That trade-off influenced nearly every modern car built over the last century. Now imagine a steel that refuses to follow those rules. A new automotive material has entered large-scale production with tensile strength reaching around 2,200 megapascals, while allowing manufacturers to reduce panel thickness and lower vehicle weight without compromising structural integrity. In some applications, it has enabled body components to become significantly lighter while delivering even greater crash protection. For engineers, that combination once belonged more to theory than to factory production, but the numbers themselves are only part of the story. What makes this breakthrough remarkable isn't simply that the steel is stronger, it's that it changes how a vehicle can be engineered from the ground up, allowing designers to rethink the relationship between safety, efficiency, and weight, at a time when electric vehicles are becoming heavier with every new battery generation. The most surprising part is that this achievement didn't make international headlines when it happened. Instead, it quietly moved from research laboratories into real production lines, while much of the global automotive industry was still designing around the old limitations. So, how did one of the biggest advances in automotive steel remain largely unnoticed outside the metallurgy world? That answer begins with an engineering challenge many experts believed had already reached its limit. For most of modern automotive history, steel development revolved around a simple compromise. Improving one property almost always meant weakening another. Engineers could increase a material's strength, but doing so often made it more brittle and difficult to stamp into complex vehicle components. Alternatively, they could improve flexibility, but at the expense of crash resistance. This balancing act became one of the defining challenges in automotive manufacturing. As governments introduced stricter safety regulations and fuel economy standards, automakers needed lighter vehicles without sacrificing structural protection. Traditional steels were no longer enough, leading to the development of advanced high-strength steel, commonly known as AHSS. The first generation of these materials offered a meaningful improvement. They provided higher strength while remaining practical for large-scale manufacturing. Car makers around the world quickly adopted them for structural components, such as roof rails, pillars, and door reinforcements. However, these steels still reached a practical limit. Beyond a certain point, increasing strength caused severe cracking during the stamping process, making mass production unreliable. Researchers then introduced second-generation AHSS. On paper, these alloys looked revolutionary. They delivered exceptional combinations of strength and ductility that appeared to overcome the previous limitations. Producing them required unusually high concentrations of expensive alloying elements. Manufacturing became slower, welding grew increasingly difficult, and costs climbed well beyond what most mass-market vehicles could justify. Despite impressive laboratory performance, these materials rarely became practical solutions for high-volume automotive production. Manufacturers eventually settled into an uncomfortable compromise. Conventional steels remained affordable but heavier. Premium materials, such as aluminum and carbon fiber, reduced weight but significantly increased production costs. Advanced steels offered promise, but often proved too expensive or difficult to manufacture at scale. Over time, the industry stopped asking whether the trade-off could be eliminated. Instead, engineers focused on deciding which compromise made the most commercial sense. For decades, that limitation appeared permanent. While much of the global steel industry continued refining existing materials, another line of research was quietly progressing. Instead of trying to improve conventional steel little by little, researchers explored whether the trade-off itself could be rewritten. Their work eventually produced a new category of automotive steel that delivered something many experts had considered unrealistic. Laboratory testing demonstrated an unusual combination of extremely high strength, together with levels of formability previously associated with much softer materials. Even more surprising was its economic potential. Unlike earlier experimental steels that depended on expensive alloy compositions, this material achieved its performance using a comparatively moderate chemical design. That meant manufacturing costs remained much closer to conventional automotive steel than many engineers expected. On paper, the results seemed almost contradictory. The material demonstrated the mechanical performance associated with premium experimental alloys, while maintaining production economics far more suitable for commercial manufacturing. Yet outside specialist metallurgy circles, almost nobody noticed. There were no major international product launches or headlines declaring a revolution in automotive materials. The breakthrough remained largely confined to research publications and technical conferences, while engineers continued refining vehicles using older design assumptions. This quiet period turned out to be extremely important. Laboratory success alone means very little in heavy industry. Producing a few successful samples under controlled conditions is one challenge. Repeating those results consistently across thousands of tons of steel moving through industrial rolling mills is something entirely different. Before anyone celebrated the discovery, manufacturers needed to answer a far more practical question. Could this remarkable material survive the realities of mass production? The answer depended on something happening deep inside the metal itself. Most people assume stronger steel simply contains more carbon or additional alloying elements. In reality, the secret was not adding more material, but carefully controlling how the existing internal structure behaved under different conditions. Think of a suspension bridge. When traffic is light, the structure remains flexible enough to absorb movement without damage. During extreme loads, however, different parts of the bridge begin carrying greater stress to maintain stability. This new steel behaves in a surprisingly similar way. During manufacturing, portions of its microscopic structure remain intentionally stable enough to allow the metal to bend into complex automotive components without cracking. Door frames, roof supports, and structural pillars can all be stamped using conventional industrial processes. The remarkable transformation occurs only when the material experiences extreme force. During a severe collision, portions of the internal structure rapidly change into a much harder phase, exactly where impact forces concentrate. Instead of maintaining one fixed level of strength throughout its lifetime, the steel effectively reinforces itself during the moment it matters most. This mechanism allows engineers to combine two characteristics once considered incompatible. Manufacturing remains practical because the material can still be formed efficiently. At the same time, crash performance improves because the structure becomes significantly stronger under impact loading. Rather than choosing between flexibility and protection, engineers suddenly had a material capable of delivering both in different stages of its life cycle. That breakthrough solved one of metallurgy's oldest scientific challenges, but another obstacle remained. Even the most advanced steel cannot transform an industry unless manufacturers can produce it efficiently on commercial production lines. Turning an engineering breakthrough into millions of production vehicles required solving problems that had little to do with metallurgy alone. Ultra-high-strength automotive steel must be heated to extremely high temperatures before being stamped into shape. Those temperatures introduce a completely different set of engineering challenges. Without proper protection, the surface rapidly oxidizes, reducing quality and weakening the finished component. Manufacturers therefore rely on specialized protective coatings capable of surviving the entire hot forming process. Unfortunately, those coatings introduced their own complications. Some of the most effective technologies were protected by intellectual property agreements developed over many years. For manufacturers without direct access, dependence on imported coated steel increased production costs and complicated supply chains. Even more frustrating, engineers discovered that certain protective coatings could unintentionally reduce toughness after forming. Every improvement appeared to create another engineering compromise somewhere else in the manufacturing process. For years, many researchers assumed these trade-offs were unavoidable. But a closer investigation revealed that the coating itself was not actually the primary problem. The real issue existed on a microscopic level, where carbon atoms gradually concentrated along the narrow boundary between the protective layer and the steel beneath it. That tiny region, far thinner than a human hair, became the weak point responsible for much of the material's reduced toughness. Recognizing the true source of the problem completely changed the direction of research. Instead of simply applying thicker coatings or increasing alloy content, engineers began redesigning how carbon moved through that microscopic interface during manufacturing. The solution would prove just as significant as the original steel itself. And together, these two innovations would finally move an extraordinary laboratory discovery into the world of commercial automotive production. Once researchers identified where the material was actually failing, the solution became far more precise than anyone expected. For years, engineers focused on improving the protective coating itself. The assumption was simple. If the coating prevented oxidation during hot stamping, making it thicker or stronger should naturally improve the finished product. Instead, detailed microscopic analysis revealed a different story. The coating wasn't the real source of the problem. What mattered was the extremely thin boundary where the coating and the steel met. During heat treatment, carbon atoms gradually migrated into this narrow interface, creating localized regions that became unusually brittle after cooling. It was an invisible weakness hiding inside an otherwise exceptional material. Rather than adding more protective material, researchers carefully controlled how carbon moved during production. By redesigning the coating process and optimizing the interface chemistry, they prevented excessive carbon buildup while preserving the steel's exceptional strength. Ironically, the solution required less material rather than more. The redesigned coating produced a steel that resisted cracking more effectively while maintaining the extreme temperatures required for hot forming. At the same time, manufacturers reduced dependence on licensed foreign technologies by developing an alternative process suitable for domestic production. Although this improvement measured only a few microns in thickness, its industrial impact was enormous. Modern manufacturing often depends on solving problems that are almost impossible to see with the naked eye. In this case, Controlling microscopic chemistry unlocked the reliability needed for large-scale automotive production. The laboratory breakthrough had finally become practical for factories. Scientific breakthroughs only matter when they leave the laboratory. Throughout industrial history, countless promising materials have demonstrated outstanding performance under controlled testing, only to disappear because they proved too expensive or too difficult to manufacture consistently. This steel followed a different path. Steel producers worked alongside automotive manufacturers to redesign production methods around the new material rather than forcing it into existing manufacturing systems. That collaboration required adjustments across nearly every stage of production, from rolling and heat treatment to hot stamping, welding, and final quality inspection. The goal was not simply to manufacture stronger steel, it was to create a complete production ecosystem capable of delivering identical performance across thousands of vehicles every month. Once those manufacturing processes matured, the material began appearing inside commercially produced electric vehicles, particularly within structural components, responsible for absorbing crash energy. Unlike exterior body panels that focus primarily on appearance, these hidden structural members perform one of the most critical safety functions in any automobile. They manage enormous impact forces while protecting the passenger compartment during collisions. Drivers rarely notice these components because they remain concealed beneath the finished vehicle, yet they represent some of the most carefully engineered pieces of modern automotive design. What began years earlier as an experimental metallurgy project had quietly evolved into production hardware, supporting real vehicles on public roads. For the first time, one of the industry's oldest engineering compromises was no longer merely a research concept. It had become a manufacturing reality. Engineering claims carry little value without independent verification. Once production vehicles began incorporating the new steel, researchers and safety organizations evaluated whether its laboratory advantages translated into measurable real-world performance. The results were encouraging. By using ultra-high-strength structural components, manufacturers reduced the thickness of certain body parts while maintaining, or even improving, their ability to withstand severe impacts. This seemingly small change created benefits throughout the vehicle. Lower structural weight contributes directly to overall efficiency, an especially important advantage for electric vehicles carrying large battery packs. Every kilogram removed from the body structure reduces the amount of energy required to move the vehicle, improving driving range without increasing battery capacity. At the same time, stronger structural members help maintain passenger survival space during collisions by limiting cabin deformation. Instead of forcing engineers to choose between safety and efficiency, the material helped improve both objectives simultaneously. Crash evaluations also demonstrated that advanced structural steels could significantly enhance the performance of critical safety zones responsible for managing collision forces before they reached occupants. These improvements do not eliminate the importance of airbags, restraint systems, or vehicle design as a whole. Rather, they strengthen one of the vehicle's first lines of defense. This illustrates an important principle in automotive engineering. Major advances rarely come from a single dramatic invention. More often, they emerge from a series of incremental improvements that collectively reshape how vehicles perform over time. In this case, better metallurgy became another important piece of that larger engineering puzzle. The significance of this breakthrough extends well beyond a single manufacturer or even one country. Every major automaker faces the same engineering equation. Electric vehicles continue to grow heavier as battery capacity increases, while consumers and regulators expect ever higher safety standards, alongside longer driving range and improved efficiency. Meeting all three objectives simultaneously has become one of the defining challenges of modern automotive engineering. Advanced steel offers another option. It does not replace aluminum, carbon fiber, or composite materials in every application. Each material retains unique advantages depending on cost, manufacturing complexity, repairability, and structural requirements. Instead, this new generation of steel changes the competitive balance. Manufacturers now have another high-performance material capable of reducing weight while preserving affordability and large-scale production capability. However, widespread adoption will not happen overnight. Factories require specialized hot stamping equipment, updated welding technologies, advanced quality control systems, and significant capital investment before they can fully integrate these materials into existing production lines. That means the transition will likely occur gradually over many years, rather than through a sudden industry-wide transformation. History suggests this is often how major manufacturing innovations spread. They begin as specialized technologies, expand into premium products, and eventually become standard practice once production expertise and supply chains mature. If that pattern continues, today's breakthrough could quietly become tomorrow's industry norm. At first glance, this story appears to be about a stronger piece of steel. In reality, it represents something much larger. For decades, engineers accepted that automotive materials required unavoidable compromises. Greater strength usually meant reduced flexibility. Lower weight often demanded higher costs. Improving one performance metric frequently weakened another. This new generation of automotive steel demonstrates that some of those long-standing assumptions were not permanent engineering laws after all. By combining advanced metallurgy with innovative manufacturing processes, researchers and manufacturers produced a material capable of changing how future vehicles balance safety, efficiency, and structural performance. Its greatest achievement may not be the impressive strength numbers alone. The real accomplishment lies in proving that careful scientific research, combined with years of industrial development, can redefine problems once considered solved. As electric vehicles continue evolving, manufacturers will keep searching for lighter, stronger, and more efficient structural materials. Whether steel ultimately remains the dominant choice or shares that future with aluminum and advanced composites remains an open question. But one thing is already becoming clear. The next generation of automotive engineering will not be shaped solely by batteries, motors, or software. It will also depend on the materials hidden beneath the vehicle's surface. Materials that most drivers will never see, yet rely upon every time they get behind the wheel. Here at Future Structures, those quiet breakthroughs are often the ones worth watching most. If you enjoyed this analysis, let us know your thoughts in the comments. Do you believe advanced steel will continue to dominate the future of electric vehicles, or will alternative materials eventually take its place? We'd love to hear your perspective, and we'll see you in the next episode of Future Structures.